Welcome back, everybody. Today's deep dive, it's going to be about material science. I've always been fascinated by all the different materials all around us, everything from our phones,
Yeah.
to our coffee mugs. But it's kind of amazing how much we just take them for granted. So today we're going to go on a journey to uncover some of the secrets of these materials. We'll explore the different types, how their structure affects their properties, and even try to look into the future a little bit. And I'm so excited to have an expert here with us today who can help us, break down these complex concepts and really dive deep. So let's start with a simple question. What comes to mind when you hear the word materials? I'm betting you're thinking of, everyday objects,
Yeah.
like a brick wall or a silk scarf. But did you know that even something as basic as a beverage container can be made from all three primary material types? Think about it. We've got metal in an aluminum can, ceramic in a glass bottle, and then polymers in those plastic bottles. It's really amazing how each material brings its own unique advantages.
That's exactly right. And that's what makes materials science so fascinating. This incredible diversity that we see in materials around us is really all thanks to each material having its own unique set of properties.
Okay, so let's break it down a little bit. What are these basic types? Fill me in.
So, at the core of material science, we have these three primary categories:
Hmm.
metals, ceramics, and polymers. And, metals are kind of like the superstars of the materials world. I mean, they're strong, they're shiny. We use them for everything from building bridges to making airplanes. And we're talking about elements like iron, aluminum, and copper. They might have a tiny bit of other elements mixed in,
Hmm.
but it's those metallic atoms that really give them their signature strength and that really cool lustrous shine.
Okay, cool.
Then we've got ceramics. And these are a little different. They're compounds made up of metallic and non-metallic elements. And they're also all around us. Think of things like glass, porcelain, even the concrete in your driveway. So
Hmm.
lots of examples of ceramics in our daily lives.
Okay, yeah, I see it now.
And lastly, we've got polymers. You could call them the champions of flexibility. These are mostly organic compounds. They're made up of these incredibly long chain-like molecules. And that's where we get our plastics and rubbers from.
Okay, that makes sense. So we've got our metals, our ceramics, and our polymers. But what makes them so different from each other? Like, why is a metal spoon so different from a ceramic plate?
Ah, that is a great question. It all comes down to something called atomic bonding. Basically, how the atoms are arranged and connected within each material. And here's the amazing part. The way those atoms are bonded dictates pretty much every single property of the material, like how strong it is, how well it conducts heat or electricity, even how it looks.
Wow, so it's like the atomic level architecture that really determines the material's personality. Okay, let's focus on metals for a second. We know they're strong and shiny. What's happening at that atomic level that makes them that way?
So metals are all about something called metallic bonding. You can kind of picture it like a sea of electrons flowing freely among these positively charged ion cores. And it's those free-flowing electrons that make metals such fantastic conductors of both heat and electricity. They also contribute to that signature metallic shine.
Okay, that sea of electrons is such a cool image.
Right.
So what about materials where the electrons aren't as free-flowing? Like a diamond is super hard while plastic is very bendable, but they're both covalently bonded. How does that work?
You've hit on a very interesting point. You see, even though both diamond and plastic involve covalent bonding, the difference lies in the type of covalent bonds they form. It's all about how those electrons are shared between the atoms.
Okay, I think I get it.
So carbon, the element that makes up both diamond and plastic, is very versatile. It can actually form different types of bonds, which result in materials with totally different properties. So in diamond, those carbon atoms are very tightly bound together. They're in this rigid three-dimensional network. And that's what gives diamond its incredible hardness. I mean, it takes a huge amount of energy to break those bonds.
So it's like those carbon atoms are holding on to each other for dear life. No wonder it's the hardest known material.
Exactly. But then you look at plastics, the carbon atoms form these long chains that are a lot more flexible, and
Yeah.
they can actually move past each other. That's why plastics are so bendable and moldable.
Wow. So the same element, carbon, can create both a super hard material and a flexible material just by changing how its atoms are bonded together. That's incredible.
It really is. It just goes to show how important this concept of bonding is in shaping a material's properties.
Huh.
Now, another key type of bonding we should talk about is ionic bonding, and this usually happens between a metal and a nonmetal. Think about something like table salt, which is sodium chloride. So the sodium atom gives up an electron to the chlorine atom, and this creates positively and negatively charged ions. and those opposite charges attract each other, forming the ionic bond.
So it's kind of like a magnetic attraction, but at the atomic level. And that explains why salt is so brittle, right? Those strong attractions between the ions make it hard to break apart.
You got it. And this same principle applies to a lot of ceramics. Those strong ionic bonds give them their hardness and their high melting points. So here's the key takeaway. The type of bonding has a huge impact on the material's properties. Strong bonds usually mean high melting points. And it even affects things like the material's stiffness, which is how much it resists bending or deforming.
Wait a minute. So does that mean that we can design materials with specific properties just by manipulating their atomic structure, like build them from the ground up?
That's exactly what we're doing. It's a really exciting time to be in materials science. We're not just discovering new materials anymore, we're actually creating them. And speaking of creating, let's talk about some of those more advanced materials that are really pushing the boundaries of what's possible. Things like semiconductors, biomaterials, and even smart materials and nanomaterials.
Okay, those sound straight out of a science fiction movie. Smart materials, nanomaterials, things are getting futuristic. Tell me more.
So semiconductors are pretty remarkable materials. I mean, they power all of our electronics, smartphones, computers, you name it. They're not quite full-on conductors like metals, but they're not insulators like ceramics either. They kind of fall somewhere in between. And here's the really cool part. We can actually fine-tune their conductivity just by adding in tiny amounts of impurities.
So they're like the Goldilocks of materials. Not too conductive, not too insulating, but just right. And you're saying we can actually control their conductivity. That's amazing.
That's exactly right. And that precise control allows us to build these tiny, powerful chips that really are the brains of all our devices. And then we've got biomaterials. They're revolutionizing medicine. These materials are actually designed to interact with living tissue. So think about things like hip implants or artificial heart valves. They need to be incredibly biocompatible, meaning they don't cause any harmful reactions in the body.
Wow. So it's not just about strength or conductivity with biomaterials. They have to actually work in harmony with our bodies. That's a whole other level of complexity.
Absolutely. And then we have what I like to call the materials of the future, smart materials and nanomaterials.
Okay, I'm ready to have my mind blown. What are smart materials?
Basically, think of them as materials that can actually sense and respond to their environment. They might change their shape, change their position, or even change their mechanical properties based on things like temperature or magnetic fields. Imagine a bridge that could detect damage and repair itself, or clothing that adapts to changes in temperature to keep you comfortable. That's the potential of smart materials.
That's incredible. It's like something out of a sci-fi movie. Okay, what about nanomaterials? What makes them so special?
Nanomaterials are all about scale. We're talking about materials engineered at the nanometer level, which is unbelievably tiny. A nanometer is 1/100000th of a meter. To put that in perspective, it's like comparing the size of a marble to the size of the Earth.
Wow, that's tiny.
And at this incredibly small scale, materials actually start to display remarkable properties that are completely different from what they'd have at their larger size. They can become stronger, more conductive, or even change color.
So you're saying we can take everyday materials like metals, ceramics, or polymers, shrink them down to this nanoscale, and suddenly they develop superpowers.
You could say that. And these superpowers are leading to some incredible applications. Things like ultra-efficient solar cells to targeted drug delivery systems in medicine.
Wow, this is all so exciting. But I have to ask, are nanomaterials safe? I mean, they're so tiny. Could they potentially cause harm?
That's a really important question.
Yeah.
And it's one that researchers are actively looking into right now. Because nanomaterials are so small, they have a huge surface area. And that can make them very reactive. There's some concern that they could be absorbed into the body and potentially cause damage. More research is definitely needed to fully understand the potential risks involved.
Yeah, it sounds like we're venturing into uncharted territory with nanomaterials. There's so much potential, but we need to be cautious as well. So much to think about. This deep dive has been amazing, but I have one question that's been bugging me. We talked about metals having that sea of electrons, and that's why they're such great conductors. But what about those materials that are kind of somewhere between a conductor and an insulator? I remember reading something about band theory, but it always seems so complicated.
Band theory. Yeah, it's a really cool concept. It's basically a way to visualize how electrons behave in materials. It helps us understand why some materials can conduct electricity and others just can't.
Okay, I'm ready for the simplified version. Break it down for me.
All right, so imagine this. In a single atom, the electrons, they occupy these specific energy levels, kind of like those orbitals we talked about earlier. But when you bring a whole bunch of atoms together to form a solid, Those energy levels, they start to interact and overlap.
So instead of these separate energy levels, they kind of blend together.
Exactly. They form what we call energy bands, basically a continuous range of allowed energy states for the electrons.
Right.
And here's the key. It's the arrangement of these bands, and whether they're filled with electrons or not, that really determines a material's electrical conductivity.
Okay, I think I'm following so far. But how does that actually translate to a material conducting electricity or not?
Okay, so let's say you've got two energy bands. You've got the valence band, which is totally packed with electrons, and then you've got the conduction band, which is mostly empty. If there's a big energy gap between those two bands, the electrons, they just can't easily jump from the valence band to the conduction band. They get stuck, and the material acts like an insulator.
It's like an electron traffic jam. Nobody can move, so no electricity flows.
Perfect analogy.
Hmm?
Now, in a conductor, like a metal, the valence band and the conduction band, they actually overlap. There's no energy gap to hold those electrons back, so they can move around freely, conducting electricity.
So it's like a superhighway for electrons. They can just cruise along with no obstacles.
Exactly. And then we have semiconductors. That's where things get really interesting. They have this small energy gap between the valence band and the conduction band. So with a little bit of a nudge, like maybe some heat or light, a few of the electrons can actually make that jump to the conduction band. And that allows for some electrical conductivity.
Ah, so semiconductors are kind of like materials with an adjustable speed limit. We can control how much electricity flows through them.
Precisely. That's why they're so important in electronics. We can very carefully control their conductivity by adding in these tiny amounts of impurities, a process called doping. And that's what lets us create transistors, diodes, and all those miniature components that make our modern gadgets possible.
Speaking of gadgets, I can't believe we haven't even talked about polymers yet. Plastics, rubbers, I mean, they're everywhere. But to be honest, I don't really know much about what makes them tick at that molecular level.
Polymers are fascinating. Unlike metals and ceramics, where the bonding is pretty straightforward, polymers have these long chain-like molecules. And they're formed by these covalent bonds between repeating units that we call monomers.
So it's like a long chain of interconnected links, and each link is a monomer.
A perfect visual.
Yeah.
And get this, the properties of a polymer depend not only on the type of monomer, but also on how these chains are arranged and interact with each other.
Okay, but how can a simple plastic bag and a super strong Kevlar vest, they're both made from polymers, how can they be so different?
It all comes down to those intermolecular forces we briefly mentioned earlier. These are those weaker forces that act between the polymer chains, and they play a huge role in a polymer's properties. Think of it this way. Some polymers have really strong intermolecular forces, and that basically holds those chains tightly together, creating a material that's rigid and strong. Other polymers have weaker intermolecular forces, and that allows those chains to kind of slide past each other really easily. So you end up with a material that's flexible and stretchable, like rubber.
So it's like those polymers with the strong intermolecular forces are having a serious bonding party, while those with the weaker forces are just casually hanging out. It makes sense why some plastics are rock hard and others are as bendy as a gymnast.
That's a great way to put it. And those intermolecular forces, they can actually be influenced by a variety of factors. Things like temperature, pressure, even adding in other molecules. That's why you can melt some plastics and remold them, while others, they'll just decompose when heated. It all goes back to those molecular interactions.
Wow, it really is all connected. Okay, so we've covered the three main types of materials. We've explored how bonding really affects their properties. But I'm curious, is there a way to visually represent all this information about these different materials and their properties? It's kind of hard to keep track of all the details.
You're in luck. There's this amazing tool called a materials selection chart, and it does just that. These charts basically plot the values of two different properties for a wide range of materials, and it allows you to see how they compare. And then you can make an informed decision about which material is the best for whatever application you're thinking about.
So it's like a cheat sheet for material scientists.
Kind of. One of the most common charts plots stiffness versus density. You'll see that metals tend to cluster together in one region of the chart, while ceramics occupy another. And polymers, they have their own little corner.
Wait, so if I wanted to find a material that was both lightweight and stiff, I could just look at this chart and see which materials fit that description. That's super helpful.
Exactly. These charts are incredibly useful for engineers and designers. Anyone who needs to select the best materials for their products, they can visually see the trade-offs between different properties, and then they can make informed decisions based on their needs.
That's brilliant. It's like having a roadmap to navigate the vast world of materials. Now let's talk about those advanced materials, the ones that are pushing the boundaries of what's possible. Okay, so we've got these material selection charts to help guide us, but what about those really cutting edge materials, the ones that are really pushing the limits? Where do they fit into all of this?
That's what makes things really exciting. Advanced materials like those smart materials and nanomaterials we talked about, they often have properties that go way beyond those traditional categories. They might even carve out entirely new areas on those charts. They're really pushing the boundaries of what we thought was possible.
So they're like the rebels of the materials world, breaking all the rules. What are some examples of how these advanced materials are shaking things up?
Well, take shape memory alloys, for example.
Mm.
These metals are incredible. They can remember their original shape. And then they spring back to it when they're heated, even after being bent or twisted. It's like they have a superpower.
Wait, so if I bend a paperclip made from one of these shape memory alloys, it could just spring back to its original shape if I heated it up. That's wild. How is that even possible?
It all comes down to a very special transformation that happens inside the material's crystal structure. When it's heated,
Yeah.
it's like flipping a switch. The atoms rearrange themselves,
Mhm.
and then they just snap back to those original positions.
That's amazing. So what are we using these shape memory alloys for? Is it just a cool science trick? Or do they have real-world applications?
Oh, they're definitely more than just a cool trick. Shape memory alloys are being used in all kinds of things, from medical devices like stents that expand to open up blocked arteries,
Mm.
to actuators in robots and even airplanes. Imagine a robotic arm that can gently pick up really fragile objects, or airplane wings that actually change their shape to make them more efficient.
Wow, it's like science fiction is becoming reality. Okay, what about those other materials of the future we talked about? Nanomaterials. Are they living up to all the hype?
Absolutely. Nanomaterials are really revolutionizing material science. Their tiny size gives them some really remarkable properties,
Mhm.
and we're really just beginning to tap into their potential.
You mentioned before that nanomaterials could be stronger, more conductive, or even change color. But how does making a material so tiny actually change its properties?
It all boils down to surface area. When you shrink a material down to that nanoscale, the proportion of atoms that are actually on the surface, it increases a lot. And those surface atoms, they behave differently from the atoms that are buried deep inside the material.
So it's like those surface atoms are the life of the party. They're more free to interact with everything around them.
Exactly. For instance, nanomaterials are often much stronger. Because those surface atoms are bonded more tightly to their neighbors, they also tend to be more chemically reactive, which is really useful in things like catalysis.
So nanomaterials are like the tiny but mighty superheroes of the materials world. What are some of the coolest things we're seeing them used for?
Oh, the possibilities are really endless. They're already being used in things like high-performance batteries, solar cells, cutting-edge sensors, even medical treatments. Imagine things like ultra-efficient solar panels that can capture way more sunlight, or batteries that can store more energy and charge super fast. And in medicine, they're being used to deliver drugs directly to diseased cells, so you can reduce those nasty side effects and make the treatments much more effective.
This is all so incredible. It sounds like nanomaterials are going to transform so many aspects of our lives. But with all this talk about these futuristic materials, we can't forget about the environment. Are we creating all of these amazing materials at the expense of our planet? What about sustainability?
You bring up a very important point. It's something that's at the forefront of materials science today. We have this responsibility to develop materials that are not only high-performing, but also environmentally friendly.
So it's not just about making the strongest
Hmm.
or the most conductive or even the coolest material. It's about finding that balance between performance and sustainability.
Exactly. And we're actually seeing a lot of exciting progress in this area. Researchers are developing bio-based polymers. So they're made from renewable resources like plants. And they're even creating new recycling technologies so we can recover those valuable materials from electronic waste.
It sounds like materials science has this key role to play in creating a more sustainable future.
It really does. Material scientists are leading the charge. We're developing the technologies that are going to help us move toward that circular economy, where materials are reused and recycled
Yeah.
instead of just being thrown away.
Wow, this has been an amazing journey. We started with the basics of atomic bonding, and now we're talking about these mind-blowing possibilities of nanomaterials. It's just incredible to think that the materials that make up our world are constantly evolving, and scientists are really pushing the boundaries of what's possible. I'm leaving this deep dive with a sense of wonder and a whole new appreciation for the materials all around us. I mean, who knew that something as simple as pouring a cup of coffee or taking a photo could involve such intricate and fascinating science? And if scientists can design materials at the atomic level now, what incredible materials might we see in the future? Could we create materials with properties we can't even imagine right now? The possibilities really are endless. A huge thank you to you for guiding us through this complex and fascinating world. And to everyone listening, keep exploring, keep asking questions, and never lose that sense of curiosity. Until next time, happy diving.